In this video, we'll analyze how a loop rotating in a magnetic field can create a current. Below, assume the loop is rotating with a constant angular velocity. This could be because there's a crank attached to the loop, and perhaps someone is physically spinning the crank at a nice constant speed. But there are other ways to get rotation in a loop. We could attach the loop to some kind of water wheel or perhaps a wind turbine. For each of the loop positions below, the magnetic flux of the loop will always be given by BA cos theta, where B is the magnetic field, A is the area of the loop, and theta is the angle between the B field and the area vector. We'd like to draw a graph of how the magnetic flux through the loop changes with time. We also want to indicate the direction of the induced current in the loop. So we're going to have to use what we know so far about how currents get induced in wires that are moving in magnetic fields. And do you think the EMF and current generated by the setup will be AC, DC, or no current at all? Well, let's take a look at each of the different positions. This loop is rotating counterclockwise, and I've highlighted one side of the loop so that we can track it as it moves through different positions. So this is going to be the first position in time. Then we'll move to this position. We'll go halfway around the circle, 3/4 of the way, and then finally the loop comes back to the same position that it had started in. So what will the magnetic flux be like in this position? We can see that the field is cutting through the area perpendicularly, so we're getting the maximum amount of flux there. So I'm going to start up high with my flux graph. Here, when the loop lays down, its area is parallel to the B field, so we're going to have no flux there. Here we'll have flux, but I'm going to say that the flux is opposite of what it was before, because before it was coming through one direction, and now since the loop is completely rotated, it's going back through the other direction. Then the loop lays flat, and finally we come back to the same flux that we had had initially. Now, since the formula for flux is BA cosine theta, and we know that the theta is changing nice and steadily. Because of this, we're going to get a cosine graph. It could look something like that. So if our theta starts off at 0 degrees, and then it goes to 90 degrees, 180 degrees, 270, and it comes back to 360. Now we should analyze the current in the loop. We see here that our loop is rotating counterclockwise, which means that the velocity of the bars here is going to be parallel and anti-parallel to the field. Okay, so when that happens, we saw in the past that there would be no magnetic force in that situation. So in these special cases, the current is going to be 0. The same thing will happen here when the loop is perpendicular to the field once again. So we'll have I equals 0 for that, and I equals 0 here as well. These are points that we can plot on the graph. It could also be interesting to connect the wire of the loop to a galvanometer. Just to show what it reads. So the galvanometer at this time should not be deflected to the left or right because no current is flowing. But we want to use the galvanometer to check the direction because we want to see what direction current is flowing. So for that, let's zoom in here a little. What I'll do is I'll hook up a red wire to one section of the loop, and I'll hook up a black wire to the other part. That way we can keep track of which wire is which. So the red is attached to the bold segment of the loop, and it goes into the galvanometer from the left side. Will there be current in this position? And if so, what direction is the induced current? To figure this out, we should use a right-hand rule. We want to observe the direction of motion of the wires in the loop and use our right-hand rule to figure out what the induced magnetic force in the wires would be. If you use the right-hand rule on this, you'd want to point your pointer finger up, middle finger points in the direction of the field, okay, so at the top we have the pointer. Here we have the middle finger. And pointing back in space is the thumb. The motion of the wire is up. The B field direction is to the right. And pointing back in space is the magnetic force on the wire's particles. But that force is going to create a current in the wire. So what we're going to see then is a current that goes this way. If we do the right-hand rule on the left side, our pointer would be pointing down this time. And that's the direction of motion of this segment of wire. This will be our middle finger pointing in the direction of the B field. And over here we have the thumb. pointing this way along the wire. As you can see, the current that's created on the right side and the current created on the left side, they both contribute to what would be a counterclockwise current in this situation. Now, when we had used the galvanometer before, we said that when current flowed to the right, that was going to cause our needle to be deflected to the right. Okay, now when we come back to this position, we're not going to have any current anymore, but I'll draw the galvanometer either way. The red lead has to be attached to the shaded in segment, and the red lead goes in through the left of the galvanometer. The black wire needs to be attached here, and we want our current to be 0 in that position. Okay, now we want to just do the right-hand rule here one more time. This time our dark segment is moving upward, and the other segment is moving downward. So clearly we're going to get the same directions of current that we'd had before. And then we connect our galvanometer. But if you look very closely, you'll see that in position number 2 here, current was flowing out of that shaded in segment, and it was flowing into the left side of the galvanometer. You can see here, though, that the wires have crossed. And now current is flowing the opposite direction through that shaded in segment, which means that current will now be flowing to the left through the galvanometer. So which way is our needle deflected now? It's not to the right anymore, it's to the left. At the end, we come back to a current of 0. But our wires have gotten a little twisted. So, this analysis shows that the device pictured here is an alternating current AC generator. What it will do is it'll create a current that flows at first in one direction, and then the current will oscillate and flow back in the opposite direction. In order to fix the problem of crossing wires, what can happen here is we can create 2 rings, which are conducting rings, so that the wires in the connecting circuit never have to cross. And the loop will just stay in contact with the different rings as it's turned. Now, here's an important question. How does the induced voltage change with theta? Well, in this case, the voltage and the current should be in phase. So when it comes to the induced voltage, it'll follow the same pattern as the induced current. A function for the magnetic flux could be written as follows. A function for the current could be written as I equals I max sine theta. And finally, for the EMF that's induced, we can write it as a function of sine. So the type of electricity generated by this setup is AC. The reason why is because we have a loop rotating 360 degrees in a magnetic field. The type of waveforms that are produced will be sine and cosine waves. In order to start to create a DC type of electricity, one thing we can do, we can use a different type of ring setup. Here we have two rings where one ring is always in contact with a certain side of the rotor and the other ring is always in contact with the other side. If instead we use a split commutator ring, then what we can do is we can stop the direction of current from switching. It says here that at the first, third, and fifth positions, there won't be any current because the split commutator ring stops the current. But what ends up happening with the split commutator ring is this. First, we see that the current is going to be directed in a counterclockwise way. But the split commutator ring stops the red lead from always being attached to the same side of the loop. So whereas the current is counterclockwise in this case, the current is still counterclockwise over here. So our galvanometer is always deflected to the right. When that happens, what we'll see our current will start off not flowing, then it will go to a max in one particular direction. It'll come back to not flowing again when the loop goes perpendicular, and then our current will be at a max in that same direction that it was originally. Now this is not perfect DC current, certainly. We want it to be more flat. And so one way to create a current that's more steady would be, instead of using just a single loop, we could connect more loops. And so if we have multiple loops all spinning in a permanent magnetic field, then when we go to graph it, what we'll see is we'll have multiple waveforms that can all be added through superposition in order to simulate a nice DC voltage or current.